Okay, welcome AP chemistry students. Now that you have to know that you are learning chemistry from a convicted felon, I hope it's not any different for you. So anyway, we're going to continue our discussion on electrochemistry as an application of thermodynamics. So what do we got going on here? Well, we kind of finished off with this idea of when we are at standard conditions. Nothing new or surprising there. And then we start to look at what is called a standard reduction potential, E0 red. Now, if you think about this, this is a give and take thing with electrons. Reduction means gaining electrons, Gur, all right. And then remember you had a red cat, so that's going to occur at the cathode. And then losing electrons would occur, your oxidation's name was An, occurs at the anode. So you would have an E0 ox and an E0 red. So something has to lose electrons and then something else gets them. Well, here's the thing. When they talk about these, they always talk about reduction potentials. Well, the nice thing about reduction potentials is if you want to change this into an oxidation reaction, you could flip this reaction and then the electrons would be on the product side and then flip the sign to negative 0.34, and this would be E0 ox equation. Okay, so that's a pretty easy fix, and this is something that we did in general chemistry during your first year of chem. So what you have is a list here, and this is kind of how good are these guys at reduction. Well, silver is really good at it. On this list, it's the winner. The whole system is based on a hydrogen electrode, seen here, given off and having a value of 0. And you see aluminum is really bad at oxidation, so it's negative. Okay, but that means it's really good at oxidation. So when we add these arrows on the next slide, when you look at this, you can see that there's an increasing ability to attract electrons or gain electrons. These guys are good at Gur, and they're all reduction reactions. So as a reduction reaction, this is bad. But if you flip this one on the bottom here and said solid aluminum turning into aluminum ion and 3 electrons, that would be a plus 1.6, and it's very good at oxidation. But again, they always give these numbers as reduction potentials. In the back of your book, there's a page called Standard Reduction Potentials. We'll use this list, and as you will on the AP exam. But if we were going to do a little bit more and we, in the perfect world, didn't have all these days off for this and that, we'd be talking about them in a little bit more detail. So this is what I was talking about. What you do, the one that is going to be reduced will be the most positive or least negative, the biggest number. So you can write right here, big. Okay, put that word there, big. So the big number, that's going to be the one that is, so you look at your E0 red, the big one, that is the one that will be reduced. The other one will be oxidized. Now, remember, it's a red cat, and An is an oxidation. Okay, so that's why they're writing it this way. That's kind of strange, because you're like, wait a minute, reduction at the anode? Well, that's because of the thing that we had talked about, that they're always reduction potential. So if we were going to do a reduction at the anode, we'd have to flip the sign of it, and that's what this is showing right here. To be honest with you, I find this formula a little bit confusing because we just finished getting good at knowing reduction occurs at the cathode, and all of a sudden we're like, what? But that's why we're subtracting it. These things are additive, so when we subtract them, that means we're in opposite world, okay? In opposite world, you have a red and instead of a red cat. So we'll make it a little bit more clear when we do this, okay? So if you were going to say, what is the cell potential using these two, right away, you would look at, you're given two reduction potentials, and this is the one that's going to be reduced, okay? Because it's a bigger number. So the copper reaction is going to be reduction, and then that will be the cathode, and that's where the electrons will be coming toward it because they're gaining the electrons at that point. And that means at the nickel electrode, it will undergo oxidation, and it would be the opposite sign of this. So that's why I prefer this second reaction. So circle this second reaction, and as a matter of fact, I like a little shorthand notation of this E0 red plus E0 ox. Now we're in the right world, right? Hey, look at that. Ann the ox, you remember? We have an ox named Ann, and the red cat. Oh, their life is good, okay? So I think you're probably going to agree with me that this is a little bit less confusing. So this is what we had talked about. You go back and you flip the sign of the smallest one. So you don't do anything with the larger one because that is going to be reduced, but you have to find the smallest number and you flip the sign. Okay, so you add those up and you get an E0 cell equals plus, and we always put the plus sign. Remember that when you're taking the AP exam, when you're doing electrochemistry, make a note here, put a positive value. Now, this says must be a positive value. That's not necessarily true. It's if we were talking about a voltaic cell, then it will be positive. Yes. There are some reactions, as we talked about, that you have to plug in if you want them to work because they are not thermodynamically favored. If it is positive like this, and if you are using this for a battery, then it would be thermodynamically favored. Okay, so the example number 2 here, let's say you're operating a reaction between AgNO3 and solid nickel. So what you want to be able to do is use that information, and then undoubtedly on the test you'll be given a list similar to this, and you just go, oh, there's your nickel equation right there, okay? And there's my silver equation. So right now, slam dunk, silver is going to be the red. It's going to be the one that's going to be oxidized in this particular reaction. And where the heck are we? There we are, right there. Okay, sorry. So if you look at that value, nice high positive value. So silver, good at reduction. Nickel, not so good. So this is going to be oxidized in the reaction, so that one will go there, and we'll flip the sign again, and then you get the E0, the cell equals plus 1.05 volts. Okay, so this is actually a very simple problem. If you can just get that idea, that take the smallest number and flip it. That'll really help you in doing these problems. Okay, so the other way of looking at this is to balance the charges gained and lost, and you might see it in this format right here, where it's 2 silver ions plus 2 electrons gives you 2 silvers. And then notice it did not change the value. So one of the things that people sometimes forget on this is one of the few times you get to ignore the coefficients. It's kind of like, if you think about it, you're putting electrons into, let's say you're putting a golf ball into a tube. Whether you put them in 2 at a time or 1 at a time, they still can only go through there at a certain rate and speed, and it doesn't matter. The energy is compensated by, double the energy, double the electrons. It doesn't change anything. So it's the exact same problem if you double that equation. You get a more accurate and correct answer for the actual net ionic equation when you combine them. So if you were going to talk about combining these into what is the reaction for this, you'd have to remember to double it, but remember not to double this number right here. So the main focus on this page, and you should write this on here, do not double, and then circle that number. Just leave it the same. It stays the same. Even though you doubled everything, the E0 does not double. So that's a very important concept. You kind of ignore when you're doing the E0 red plus E0 ox equation. Okay, so here's one that's a little bit trickier and probably better to use this first form of the equation, because you can kind of keep the sign straight that way. So this is the one time where I think you might think it might be a little bit better to use that, because what you're given is you're given an unknown. So the problem with unknown is you don't know if silver is going to be a red or an ox. Well, chances are it's going to be the reduction potential because of that value, but you do know what the final voltage is. Okay, so we know the answer to the problem. And one of the ways of avoiding flipping signs is to use this. Now remember, red cat, this should be oxidation, but if you're using both of them as reduction potentials and you're not sure which one is which is the case here, maybe this one is whatever, we don't know if silver's over here or if silver's right there, depending on what the unknown is. There are some metals that are better reducers than silver. Just because we have that little miniature list doesn't mean that our unknown couldn't have had a reduction potential of like 1.2 volts. So that's why I think this is a little cleaner way to solve the problem. And notice all we had to do here is kind of just do a little flipperoo then of the signs on everything, and just kind of rearrange this to get this by itself. And when you want to bring that negative over there, that would be this minus the E0 of the cell. So it gets a little tricky with the pluses and the minuses, but we can then just whatever this was at the anode is 0.8 minus 0.47 volts. Okay, so and then that worked out for us. And if you would have plugged them in the other way, then you got a negative value, and this would not be a voltaic cell, because these and this is missing the plus symbol, by the way. For the final answer, make sure you put the plus in there. So add that in there. It's one of the things we might check when I check your notes. Okay, so bottom line on all this, and this is what we'll finish this lecture up with. If the E0 is greater than 0, it's thermodynamically favored. But sometimes you can have a negative E0. And if you think about that, that should be upsetting you, because we're changing the sign of the smaller one. How would that be possible? It should always be positive. But Hang on, we'll tell you that on the next lecture.